Another way we can balance oxidation reduction problems is with the half reaction method. And this is taken from Kendall Hunt. This half reaction method is a method of balancing even the most complex redox equations. What you do with half reaction is you split the redox reaction into half reactions, a reduction half reaction, and an oxidation half reaction. So half reactions, redox reactions can be split in half into a reduction reaction and an oxidation reaction. Example here, we have HCl plus magnesium goes to magnesium chloride plus hydrogen gas. We can split those two, an oxidation reaction and a reduction reaction. Then when we split them up, it makes it easier to balance. Then we put them back together. Redox reactions in an acid or base, there's different roles, so we have to go through these roles. The half reaction method occurs in either an acid or acidic or basic environment. Now, this method uses a species produced by the acids or bases to balance the equation. Species produced, hydrogen and oxygen. Acidic redox balances with hydrogen and water. So if we want to balance hydrogen, we add protons, H+. If we're going to balance the oxygen, we're going to add water. In a basic environment, we balance also with hydrogen and oxygen, but in a basic environment, we're going to balance the hydrogens with water, and we're going to balance the oxygens with hydroxides. How do we do this? We're going to determine oxidation numbers and use to decide what's being reduced and oxidized. Let's look at this example. Oxidation numbers of oxygen is -2. Of manganese has to be +7 because we have this negative sign here. So that will add up to a -1. On the next compound, hydrogen is +1, oxygen is -2. The carbon thus must be +3 or a +2. Now manganese, normally, if it was by itself, it would be an oxidation number of 0. But we see that it has a 2+ charge. So that oxidation number of manganese is a +2. And the next one, oxygen, is -2. In this case, the carbon would be a +4. We see that manganese was reduced. It gained electrons in order to go from a +7 to +2. Oxidation occurred from the carbon going from a +3 to a +4. It lost an electron to go from that charge. So what we're going to do first, we're going to split the reaction into half reactions, one for oxidation and one for reduction. The elements that were reduced, we'll split it like this. That was the manganese. And we have the one that was oxidized. Now, we're going to perform each of these steps for both half reactions. We're going to balance all the atoms except hydrogen and oxygen. These will come later. So the first one we see, well, manganese is already balanced. So we have one reactant, one product of manganese. But with oxygen, we have 4, and we don't have any oxygens here, but we're going to leave that for now. And we're going to take care of that later. The reactant for the half reaction that is being oxidized, carbon, oxygen, and hydrogen. Carbon has 2 on the reactant side and 1 on the product side. It has 4 oxygens on the reactant side and 2 on the product side. And has 2 hydrogens on the reactant side and no hydrogens on the products. So we're going to balance everything except oxygen and hydrogen, which just means we're going to balance the carbon. So we're putting a 2 there. So that means we are balanced with carbon. And what that does is it balances the oxygen as well. We now have 4 oxygen on the reactants and product side. Now we're going to balance the oxygens by adding water to the side needing more oxygen. So we see on the first reaction that the products are going to need more water. Or excuse me, they're going to need more oxygen, so we're going to add water to that side. 4 waters. Why did we add 4 waters? Well, because we needed 4 oxygens, so we had to add 4 waters. So now we have 4 oxygens on both sides. And we have 8 hydrogens. Because we added the water, we have now 8 hydrogens on the product side as well. So the oxygens are balanced on both reactions, on both half reactions they are balanced. But the hydrogens are not. So then we go to the next step. We're going to balance the hydrogens by adding the proton, H plus, to the side needing more hydrogens. And this is a mistake here. That should be an 8. We're going to fix this little mistake on the PowerPoint. There's 8 hydrogens on that side. So what are we going to do? Add protons. We're going to add 8 protons, and now we have 8. So we are balanced with the protons on the hydrogens. Go to the next reaction here. We can see we have 2 hydrogens there, so we on the other side must add 2 protons, and now that is balanced. All right, so everything is balanced. All the things are balanced. Now we go to the next step. All the elements are balanced, but the charges might not be balanced. So we have to find the total charge on both sides. Because we added the protons, that might throw off all the charges. So we're going to add negative charge now, because we just added positive charge with the protons. We're going to add electrons to balance the charges. So let's look at charge. So on this side, it's a +7. On this side, it's a +2. So we're going to have to get rid of 5 positive charges there. So that means we're going to have to add electrons by adding 5 electrons. So now the charge for this half reaction should be +2 on both sides. And there we go. Next reaction, charge on the reactants is neutral, but the charge on the product is a +2. So that means we're going to have to add electrons on this side. Wherever we need negative charge, we're going to have to add the negative charge to get it down to neutral for this case. So that means we have to add 2 electrons on the product side, and now we're all good. So electrons should need to be added to the reactants in the reduction half reaction. So added to the reactants in the reduction half reaction. So remember, that was the one that was being reduced, and this was the one that was being oxidized. And to the products in the oxidation half reaction. So really, you don't even have to think about it. You can just say, okay, well, I'm going to have to add electrons to the reactants of the reduced half reaction and the products of the oxidized half reaction. Now what we do is we multiply the half reactions by a factor to make the electrons lost in the oxidation, in this case, equal to the electrons gained in the reduction, in that case. So what factor would that be between 2 and 5? Well, we have to do a lowest common multiple. So that means we have to add or multiply 2 by this one, and we get 2 over here, or excuse me, 5, and we get 5 on this side. Lowest common multiple, which would be 10. And then we add the 2 half reactions back together. And this is what we get way down here. So when we added all these, when we multiplied these together, that means we multiply the 5 electrons by it, the 8 by 2, manganese by 2, all these by 2. This one we multiply everything by 5. We distribute it, and we can see what we got here, this big long equation. But we're not done yet. We have one more step. We're going to cancel out anything that appears equally on both sides. So the 10 electrons we can cancel out. The 16 hydrogens there can cancel out with 10 here, but we're left with 6. And that looks like it's all what we can do to cancel it out. And this is the final balanced equation. So you can see what a bear that is. And it would have been pretty intense just to try and balance that in a normal fashion. Okay, let's try another one and an acidic solution. First, before we even write half reactions, we're going to have to decide which is being oxidized, what is being reduced. So we write the oxidation numbers. Tin, we can see if it's by itself, it's normally 0, but it has a charge of 2 plus, so it's going to be +2. Oxygen is -2. -2 times 3 is a -6, but it has an overall charge of minus here, so this has to be a +5. And on this side, it's already given, it's going to be a +4. And then iodine on this side is a -1, already given. So let's see what is being reduced and oxidized. So tin goes from a +2 to a +4. So we lost electrons there, it's oxidized. Iodine, we went from a +5 down to a -1, so we gained electrons. That is being reduced. So now we can write our half reactions. So let's do the reduction one first. that, remember, was the iodine. So that was iodine, 3 oxygens, go to iodine. And then we have the oxidation one. We have tin going to tin. So we wrote the half reactions there. So now we balance the half reactions with respect to the atoms involved, except hydrogen and oxygen. Well, the iodine here is balanced and the tin here is balanced. Well, those are already balanced, so we don't have to balance those yet, or we don't have to balance those at all. So we'll go on to step 3. Now let's balance the oxygens by adding water molecules to the side that needs more oxygens. So on the reduction side, we can see that we're going to need 3 more oxygens, so we're going to add 3 waters, so we can get 3 more oxygens. And we don't need to do that on the oxidation reaction, so we're good to go there. And then we'll go on to the next step. Now we're going to balance the hydrogen atoms by adding protons to the side that needs more hydrogen atoms. In the reduction one, we can see that we're going to need more. We're going to need 6 more hydrogens on that side, so we're going to add 6 hydrogens plus this. So we're going to have equal hydrogens now. We have equal oxygens and we're going to have equal hydrogens. And on the oxidation one, no, we don't have to do anything. We're all good there. So let's go on to the next step. All right, now we balance the charges by adding electrons to one side or the other. Because we added hydrogen, we're going to now have to add electrons to balance those charges out. And we can see here that on the left side of the reactant, if we add 6 electrons, that'll take care of the hydrogens here. So we'll be having a balanced total charge of -1 on the reactants and -1 on the products. So as long as it's balanced, it doesn't have to be neutral, we just want it to be balanced. And on the oxidation reaction, we finally get to do something, and we have to add 2 electrons here. So then we'll have a total charge of +2. Alrighty, so let's now balance the electron change in the 2 half reactions by multiplying the 2 reactions by the least common multiple. So we see there's a 6 electrons here and a 2 electrons here. That means we're going to have to multiply by the least common multiple, which would be 6. So we'll multiply this one by 3. The upper one, we don't have to do anything. That has the lowest common multiple. Well, we multiply by 1. So we multiply everything by 3. And there we have 2 half reaction. And we do that so we can, at the end, balance out or cancel out the electrons. So then we go on to the next step. We're going to add these 2 half reactions back together. Okay, so we added these 2 half reactions back together. Now what we can do is go on to the next step and just cross everything out. So we're canceling things out that appear on both sides of the equation. So we see the electrons here. That's the reason why we multiplied by the lowest common multiple, so we can get rid of them, because we really don't want those in an equation. And there we go. That's our final balanced equation. There's nothing else that we can cancel out or get rid of, and that would be it. So now let's go on and try the bases.